So our third talk is from our co-founder of Confluent, Jun Rao, who will give us a deep dive on Kafka Controller, which is a single entry point for all kinds of administrative requests to a Kafka cluster. And in the old versions of Kafka, the Kafka Controller has been reported as one of the main factors for limiting Kafka cluster scale. So Jun Rao tonight is going to talk about all kinds of improvements that the community and Confluent has been doing to basically limit that, to lift that limit of Kafka Controller in a cluster.
Okay. Thanks, everyone. Before I start, can I do a quick show and how many people here have used Kafka in production? I guess pretty much everybody. All right. Okay. Okay. So sounds good. So what I'm going to do today, I'm going to talk about the control. What is controller in Kafka? What are some of the common things a controller does? And what are some of the common problems we have seen before? And what are the things we have done to improve it? So to talk about controller, the first thing we have to understand a bit is how Kafka replication works. This is actually the replication within the Kafka cluster, right? So when you publish data in a Kafka topic today, we allow you to store the data redundantly in multiple copies. Those different copies will be stored in different brokers. So this picture shows you a little bit how this works. So this is a picture shows you have a class of 4 brokers. And in this case, we have replication factor 3. So if each of those little box corresponds to a replica for a partition, those little boxes are the same color, they correspond to the same partition, but different replicas, right? As you can see, after you create this topic, the replicas of those different partitions are sort of distributed across all the brokers. If any of those broker goes down, there's another live replica that has exactly the same data that can serve the same data. So that gives you higher availability and potentially durability as well. Now, a little bit more detail how this works. If you zoom into a particular partition, right, this shows we have these 3 replicas just for one partition. So in this case, one of the replica, in this case, the replica on broker 1 will be designated as the leader. The other 2 replicas will be the followers. So the flow is all the writes will go to the leader replica. So the leader replica will take it and write to its local log. All the followers, they just ask the leader for new data. And then once you get the data from the leader, you will write the data in exactly the same order the leader has decided in its local log, and the follower will write the same data on its log. So, so over time, I think all the replicas will have exactly the same data in exactly the same order the leader has decided. And we can, if you have a producer, you can decide when the producer will get acknowledgement of the data. The producer can either just wait for the leader to get it, but if you want the data to be persisted and not to be lost after any leader failure, you can also choose to wait until the data is fully replicated to all the replicas. So that's sort of the other mode. In any case, the way we expose the data to the consumer is only when the data is fully committed, meaning that the data is actually fully replicated to the leader and the follower. That's when we will expose the data to the readers. So the reader always sees committed data and it's always consistent, because every time when the leader fails, you can always switch to another replica. It's guaranteed to have the previously committed data. So that's sort of a little bit at a high level how the replication works. As you can see, we do have this concept of leaders and followers, and when the leader fails, we need some logic to select who should be the new leader, right? So that's essentially the role of the controller. So this is a high-level description of what a controller does. First thing, there's only a single controller per Kafka cluster. There's not a separate process. It's actually embedded in one of the brokers. So one of the brokers acts as a controller for the whole cluster. The controller does a couple of things. The first thing it does is it has to monitor the liveness of every broker in the whole cluster, because it has to know which one is alive, which one is down, and then it can act on that. The second thing, which is also important, is on those broker changes, if one of the partition's leader is no longer alive, the controller is responsible for electing the new leader. And once that decision has been made, the controller is also responsible for propagating this information to the rest of the brokers in the whole cluster, so that the broker has the new information about how to serve the data. Next, I'm going to walk you through just a little bit on some of the important things the controller has to do. The first thing is how is the controller elected? Well, the way we elect controller is there's like a path in Zookeeper, which is written here, /controller. There's a single path there. Every time when you bring up a broker, every broker will try to write itself, its value, to this controller path. Of course, only one of the brokers can win the creation of this path, right? Because if the path already exists, you can't create the same path again, you'll get an exception. So whoever wins that creation becomes the controller. In this case, the first broker, broker 0, wins that path, so it's the controller. It actually writes a little bit about itself, the metadata in this path, so that we know who is the controller. Okay, the second thing we need to talk about is there's certain metadata state at the class level. For simplicity, for each of the topic partition, we have to maintain a little bit of metadata about this partition. And the most important thing, of course, is who is the current leader of this partition. There's also some other things like which replicas are in sync. That's also part of the metadata. So I just didn't write it down on the slide. So all this information are pretty mission critical, right? It's partition level metadata. This information, because it's mission critical, we need to store the information such that it can survive individual broker failures. So currently, all this metadata are persisted in Zookeeper. So each of this partitions data is persisted in a separate path in Zookeeper. But the controller also needs information for responding to client requests and to propagate this information when the broker is restarted. So for efficiency, the controller also has an in-memory cache of the same data. So it caches this in its Java heap memory in the controller broker. So that's the second thing, which is the controller has some states that it has to manage for the whole cluster. And of course, this state is backed by a persistent Zookeeper. Next, let's walk through some of the common operations the controller has to do. The first thing the controller does is to react to some broker failures. The most common failure of a broker is what we call this control failure, meaning that the broker actually is fine. There's nothing wrong with the broker, but an administrator wants to stop the broker because they can push in some new configurations or maybe deploying new code. Right? So we have some logic to make that process faster to minimize the impact to the client when you have this kind of control failure. So this slide describes a little bit the process, what happens. So the first thing we do is if you want to shut down a broker, let's say in this case, broker 1, what we'll do is we'll send a SIGTERM signal in step 1 to this broker. So once this broker received the SIGTERM signal, it will send the internal request to the controller to indicate to the controller that it's intending to shut down. Now, once the controller receives this, it has to act on that. In particular, it has to do some selection for the leader for those partitions that are about to shut down. So in this case, we can see on this broker 1, which is about to shut down, it has 2 partitions, both of which it's the leader for those. Of course, we know when this broker goes down, it cannot be the leader. So what we want to do is we want to do this a little bit proactively, meaning that before this broker actually goes down, broker 1 goes down, we want to move the leader of these 2 partitions to some other brokers so that hopefully by the time it shuts down, there's no impact to the live traffic. So that's what a controller does in step 3. it has to change the leader for these two partitions. And in this case, broker 2 is actually alive, and it actually has a replica for both partitions. So in this case, the controller will change the leader for both partitions from broker 1 to broker 2. Before it does that, it has to do a couple of things. One is, because this is actually pretty critical metadata, right? It has to persist that. So the first thing it has to do is to write both information to Zookeeper. So once this is persisted, we know this information can't be lost. Then the controller can communicate this information about new leader to the rest of brokers, in this case, broker 2. And at that point, it can also acknowledge the broker 1, who is the one who initiated the control shutdown request. Now the control shutdown can complete, broker 1 can now shut down. But at that point, since we have moved the leader already away from broker 1, so there's no traffic to broker 1. So actually shutting down broker is fine because it's not really impacting the client. So that's sort of the overall of the control shutdown logic. What are some of the issues with this in some of the earlier versions of Kafka? Well, there are a couple of issues. The first issue is, remember in step 3, what we have to, the controller has to do is the controller has to persist all the new information about the leader, right, for each of those topic partitions whose leader has changed to Zookeeper. And in the earlier version, this persisting step, it's serial, meaning that we'll write one partition's new value to Zookeeper, wait until it completes, and then proceed to the next partition. So if you have lots of partitions, the total amount of time it takes can be long, right? So that will just impact the amount of time a broker can shut down in a controlled way and can affect, for example, your whole cluster's rolling restart time. So that's the first issue. The second issue is the communication from the controller to other brokers of those new metadata, who is the new leader. In some of the earlier versions, this communication is not batched. So we actually will send just a single remote request for each partition. So one of the issues is, if you have lots of partitions, right, you end up with lots of small requests queued up to a broker, and each request takes a bit of time, CPU time, for the broker to be processed. So that can also add up. That can impact the load on the broker. So these are sort of two problems with the control shutdown. I'll talk about what are the things we did to improve that just a little bit later. The second thing the controller often does is the controller failover. So when you do a rolling restart of whole cluster, right, at some point you have to restart the controller broker. So now when the controller fails, of course, we need a process to select another broker who is alive as new controller. Right? So that's what the processes do. Let's say in this case, broker 0 was the older controller. Let's say it fails. Of course, after it fails, this pass in Zookeeper, because it's like an ephemeral pass, it will be gone. So now everybody will be notified there's no longer a controller for the whole cluster. Now they will all be trying to select themselves as the new controller by trying to write to that pass. So let's say another broker, in this case, broker 2, wins that creation. So now broker 2 is the new controller. So this all happens automatically, right, without any human intervention. But one of the things this new controller has to do is to load up its state. Because remember earlier, I mentioned we have all those persistent state, right, in Zookeeper about the metadata for each of those topic partitions. This is actually pretty critical information. For the controller to start working as a controller, it actually needs to have all the states loaded in memory. So in this phase, in this case, when you have to fail over a controller, the first thing the new controller has to do is to load up all the partition level states in its memory before it can act as new controller. So that's sort of one of the important things in the controller failover. Now, what are some of the issues with the controller failover in some of the earlier versions of Kafka? Well, there are a couple. The first issue is the reads from from Zookeeper into this new controller is also similar to before. It's read sort of serially. We read it like one partition at a time. So again, if you have lots of partitions, this can add up. And this is actually important in the sense because when the controller has to fail over, it actually has to read all the partitions in the cluster, not just the partitions that it locally has, because it actually needs to see the state for the whole cluster. So if you have lots of partitions at a cluster level, this process can also take long. And the impact, of course, the longer it takes, the more delayed the controller will be before it can do its useful things like electing new leaders. So this can also affect the availability of the cluster if you have if this process is long. Another issue we had is actually a little bit related to the older controller. So in the common case, when you have the controller fail over, the old controller is actually really gone. So it can't do any other things, right? Once you have a new controller. But in some rare cases, it could be maybe the old controller didn't really physically die. It could be it had a long GC, garbage collection, right? So then because of that, it can also lose its session to the Zookeeper server. In this case, the Zookeeper server can treat this broker as temporarily gone, and then a new controller will be elected. Now the question is, what happens when this old controller wakes up from a long GC, right? Because now there's a new controller that's acting. We don't really want the old controller to be interfering with the new leader. Since some of the older version of Kafka, the fencing logic is a little bit weak. So in some of the rare cases, it can be when that old controller wakes up from a GC, it may be doing something that's a little bit in conflict with the new controller. So then it can lead to inconsistency at the cluster level. So that's another issue. Next, I'm going to talk about some of the improvements we have done in this space. The first thing is some of the performance improvements we did. This is actually in Apache Kafka 1.1. It's about like a year and a half ago. So one of the things we did is to improve the way how the controller interacts with Zookeeper by doing reads or writes. So remember earlier when I talked about some of the performance issues is a lot of the things we do with Zookeeper is like serial. So here, let's say if we want to write 4 partitions of data, right, over here, we'll wait for the first partition's metadata to be completed and then move on to the next partition. In the improved version, we just made that more pipelined. So we use this sort of asynchronous pipeline API in Zookeeper. So if you want to write multiple partitions, right, we'll be initiating the write for the first partition. Before it completes, we'll initiate the second one, we'll initiate the third one. And then as those things are happening, some of the things can be potentially be batched together and then be done in parallel. And in the end, we'll say, okay, we'll wait for everything to be completed. As you can see, because we are doing this pipelining, the overall latency can be shortened a lot, especially when you have more partitions. So that's the first thing we did to improve the performance. The second thing we did is when the controller has to communicate this metadata to other brokers, we also batch the communication. So instead of sending one partition in a single request to other brokers, the controller now will send hopefully just a single request, including all the partitions. So that also reduced the amount of requests each broker has to handle when you have this failover. Okay, so now let's look at some of the improvements where this happens. So the first thing, let's revisit back to this control shutdown process. Remember earlier, we have this bottleneck in step 3. That's when we have to persist all those metadata, right, during a control shutdown to Zookeeper. So after Apache Kafka 1.1, all the writes to this are pipeline. So this is actually a big improvement to this step. And the communication from the controller to other brokers, that's also batched. That also improves the second part of the control shutdown. If we look at controller failover, when the controller fails over, it has to read this data from Zookeeper into its memory. And this process is also using that pipeline reads from Zookeeper. So we can hide a lot of latencies in Zookeeper. Now let's look at some of the performance numbers we have. So we did some performance just to see how big of an impact we have with those changes. So these are some setup numbers. We have like a 5-node Zookeeper, 5-node broker, roughly tens of thousands of partitions, and for each broker we have about 10K partitions or replicas. So the first set we did is to measure the time to do a controlled shutdown of a single broker with this setup. So before 1.1, this process can take more than 6 minutes because you have tens of thousands of partitions to move. With this fix we had in 1.1, it takes 3 seconds. So it's a big improvement. The second thing we did is to measure the time to complete the controlled failover. A big part of that is for the controller to finish the loading of those states, right, from Zookeeper. So again, this is some setup, and remember in this case, during the failover, the controller has to load all the partitions metadata for the whole cluster into its cache. And in this case, it's about 2K topics times 50 partitions, is about 100K worth of partitions it has to load from Zookeeper. So these are some numbers we have. So before we did improvements, this process takes about 28 seconds. With the improvements, by pipelining those reads from Zookeeper, we can cut it by half. So it's also a big improvement. So next, I'm going to talk about some of the improvements we did in terms of fencing those zombie requests from the controller. So there are a few different flavors of fencing we have to do. The first level is the zombie request can be because the controller itself was zombie. So I sort of gave you an example earlier. So it is possible that a controller can lose its controllership because, not because it's like actually failed. It could be because it actually had a long garbage collection. So that's one case. In this case, we need to make sure when this controller wakes up from the GC, it can't do any damage, right, to the cluster. It can't send zombie requests. It can't write any zombie data to Zookeeper. So that's actually we already did in Kafka 1.1 as part of the usage of a new set of Zookeeper API to allow us to do the pipelining. Another thing we did is maybe the older controller is live, but you can have some administrator comes in, manually deleted that controller path in Zookeeper. In this case, that will also trigger the election of new controller. And in that case, the older controller hasn't even lost its session. It just magically it's not the controller because something has changed undercover beneath it. So in that case, we also want to make sure as soon as the new controller is elected, the old controller, even though it's alive, it can't do any damage to the whole cluster. So this is done by a couple of things. One is we added a little bit logic how the controller persists its metadata to Zookeeper. So with the change in Kafka 2.2, to be able for a controller to successfully write a value to Zookeeper, you have to make sure the controller epoch you cached in memory matches the controller version, the controller epoch that's actually written in Zookeeper. So there's a separate path in Zookeeper where we register the latest version of the controller. So every time the controller changes, the controller has to bump up that version. And each of the controller actually keeps that version in memory. So when you try to write to Zookeeper, the Zookeeper have this API for you to do this conditional write. You can associate a condition with a write, and then the Zookeeper server makes sure it checks that condition. Only that condition passes where the write be allowed. So in this case, we just change logic so that all the writes the controller will be doing will be conditioned on a matching controller epoch. So with this, we can fence all the zombie writes from the old controller to Zookeeper. Of course, all the requests from the controller also carries this controller epoch so that the broker can also fence the older version of the controller request as soon as it has seen the new ones. Another type of zombie request that's actually getting a bit tricky is, in that case, the controller may be okay. The controller is actually the right one. But in the case when you have restarted a broker, so when the broker is restarted, it could be that the broker is receiving a request from the controller, but that request is based on what the controller generated based on the older restart of that broker. So maybe I think when the controller was responding to an event for one broker and is about to send it, and this broker goes down and the broker comes back again. Now this broker is actually receiving something from the right controller, but it's actually based on its previous generation of the restart of broker. So in some sense, that can carry information that's not suitable for this current restart of the broker. So earlier, I think we didn't really have a way to distinguish that, but we also fixed that in Kafka 2.2. So the way we do that is we also added a epoch for the broker. So now every time a broker is restarted, the broker will be registered with a new epoch. So then we can distinguish between two different versions or two different generations of the broker. And we can decide, based on that, we can decide either to take a request from the controller or ignore it. So this will allows us to be more protective in terms of those zombie requests, even from the right controller. Okay, so to summarize, so these are some of the improvements we have done in some of the recent versions of Apache Kafka. We made a lot of improvements, both in terms of performance as well as correctness. So now I think the controller is in a much better state in terms of scalability and consistency and correctness. So before I open up for questions, these are set of people who have contributed to all those work that I presented earlier. I think some of them probably are sitting in this audience. So I just want to give them like a big applause, and then we can take some questions.
So for the benchmark you did, have you tried to see for a large number of brokers in your cluster, how the performance number will be different, or it is like relevant or not?
Yeah, I think we haven't tried this on a large number of brokers. My expectation is the result won't necessarily be changed too much, because I think there are two things that's important. When you do the control shutdown, what really matters is the number of partitions that's assigned to this shutting down broker. That's sort of irrespective of the size of the cluster in terms of brokers. The second thing is the controller failover time. That is mostly just proportional to the total number of partitions in the whole cluster. Now, whether it's in a fewer number of brokers or sort of more number of brokers is sort of a secondary. But in general, it is true, the more partitions you have in the whole cluster, typically you need more brokers. So it is correlated a little bit in that way. Yeah, thank you. Any other questions?
I had a question. So I'm curious what you think the scalability bottlenecks are to getting to like thousands of brokers or like millions or tens of millions of partitions. Like where do you think the bottleneck for that is?
Yeah, that's a good question. Okay, so so in terms of scalability, of course, I think longer term we want to make further improvements to make sure we can scale up to more partitions at the cluster level. Now, there are a couple of things to consider. I think one is some of the just the raw latency, right? I think earlier, I mentioned when you have this controller failover, you still need to wait for that controller to load up, right? Or the metadata in memory before it can work as a controller. So that, I think we improved that, but I think in the case you have a hard failure of the controller, you still need to wait for that amount of time, right? That's in some sense proportional to the number of partitions. So, so one way we can do to improve that is, if we can make that part active as well, right? If you can have another sort of a broker that can be more actively caching the same metadata, then in the case when you have a controller failure, you don't really have to wait for that latency because it's warmed up already, right? So that can improve the scalability sort of a lot from that perspective. Then another aspect is now how do you sort of communicate that metadata, right, from the controller to the broker? So today, when a broker is restarted, initially the broker has no metadata because it has to get everything from the controller, right? So, so of course, the more partitions you have, the more information the controller has to communicate that to the broker, right? And at some point, that just means you need like you need a large remote request to be able to propagate this metadata. So that's a second thing that's sort of related. So there, I think, but if you can imagine that if we can make that part more incremental, then potentially we can also scale up the scalability in terms of the absolute number of partitions you can have per broker. So I think if we continue with our current path with some incremental changes, we can potentially scale up to maybe probably close to million level partitions. I think if we make a lot of the parts more incremental, where we don't have to necessarily send the whole thing every time a broker restarted, I think we can probably make that number even bigger. Any other questions?
Hi, have you considered using some formal methods to verify the algorithm in some way and proactively find some kind of edge cases?
Yeah, that's actually a good question. I think, yeah, I think Jason from Confluent, he actually gave a pretty well-received talk at last Kafka Summit in San Francisco. A big part of that is about using some formal replication verification of Kafka's replication model. So a lot of that is based on Lamport's replication state machine. And we actually did find quite a few real bugs that we haven't captured with all our system tests. So, but the model captured that. So we have made a lot of improvements based on that. And I think pretty much all those have been contributed back to AK. So now I think at least if you run the same model check, it actually can stay there for probably hours. Earlier, I think, because this model check can verify the states very quickly, right? It can probably check millions of those states in just in just a few seconds. And earlier, I think we were probably just hit the issue maybe just a few seconds when we start running this. Now, I think the model won't fail for hours. Any other questions? There's one there in the back.
Is there any plans to use the data from KIP 380 to facilitate rolling updates in the future for zero downtime upgrades?
Yeah, actually, could you remind me of what's KIP 380?
Just one slide back, the EPA.
It's on.
2 slides? Yeah.
Okay. To do
rolling updates, in-place updates, live with no downtime.
No down. Well, today if you have redundancy, right? You actually can do rolling upgrades already with all the controlled shutdown logic. You know, you can bring any broker down, but we'll make sure the other replica takes over the serving of the data right before you actually shut it down. So this is actually pretty standard rolling upgrade procedure, and I think you need that a little bit just to prevent the case where you are restarting a broker too quickly. So that definitely helps. But other than that, I think the rolling the standard rolling restart of the cluster should already be helpful in terms of making the cluster highly available.
Maybe I can add a few words about the upgrades. So in our Apache Kafka webpage, we actually have the upgrade section whenever a new major or minor release was being out, basically. And besides the rolling bounce manner, maybe one tricky thing that people have to be aware of is that whenever there is an internal protocol change, then you probably need to consider doing 2 rolling bounces where you have to stick with the old internal protocol and then doing a second rolling bounce, upgrading the new protocol. But generally speaking, you should not have downtime upgrading your Kafka brokers. Okay, cool. Any other questions? Okay, so let's thank Jun again.
Thanks. Thank you.
Yeah, and I want to thank everyone for coming to our first Confluent Kafka Meetup as well. And of course, in the future, we are going to host more Kafka meetups in both our Palo Alto headquarters as well as in our San Francisco office, where we can share the cutting-edge work that Confluent has been working with the community on Apache Kafka as well as its ecosystems, operations, and stuff. So we are looking forward to see you again in the future events. Thank you.